Next topic, let us see a problem on forced convection through external flow over plates. So this is the problem. An air at 25 degrees Celsius flows over 1 meter and 3 meter. In that, the 3 meter is the length of an horizontal plate maintaining at 200 degrees Celsius at 10 meter per second. Calculate the average heat transfer coefficient for both the laminar and turbulent region. Take the critical Reynolds number value is 3.5 into 10 power 4. So we are solving a problem on a horizontal plate of an dimensions of 1 meter and 3 meter. In that, the 3 meter is the long. They given us 3 meter is long. Therefore, in a given data, we taken length as 3 meter, and they given the temperature value as 25 degrees Celsius. That is the fluid temperature. The fluid temperature is denoted by T infinity, 25 degrees Celsius. And then maintaining the horizontal plate is maintaining at a temperature 200 degrees Celsius. Therefore, the plate temperature is denoted by TW, the plate temperature, wall temperature, surface temperature. These terms will be denoted by TW, that is 200 degrees Celsius. And the critical Reynolds number is 3.5 into 10 power 5, and the velocity of the fluid 10 meter per second. So first we need to know how we have to identify whether the problem comes under a free convection or forced convection. When in a problem, in a given data, when the velocity value is given, it comes under the forced convection problem. If the velocity value is not given in a problem, comes under a free convection problem. Why? Why? Because in a forced convection, the external forces by means of a blower or compressor, we are giving an external forces to a fluid in order to move the fluid from one place to another. In order to move in order to change the heat, you need to give an external forces. Therefore, the velocity value is given. So we can identify the velocity value given. It is forced convection. And we need to in this problem, we need to calculate the average heat transfer coefficient for laminar and turbulent. The average heat transfer coefficient denoted by H. Therefore, the H for a laminar to turbulent we need to solve. For all the problem, we need to find the TF value, that is film temperature, the average of this wall temperature and fluid temperature. Therefore, TW plus T divided by 2 is 200 plus 25 divided by 2 is 112.5 degrees Celsius. So by this temperature, we need to take the property of air, because here the air is the medium. So therefore, from the HMT data book at page number 34, by seeing 112.5 degrees Celsius, we need to write all the parameters. That is the density, kinematic viscosity, Prandtl number, and thermal conductivity values for these 112.5 degrees Celsius. By this, we need to identify whether it is laminar flow or turbulent flow. For that, we need to find the Reynolds number value. Therefore, it is a problems on plate. Therefore, U L by gamma. Therefore, U is 110, and L is 3. The gamma is, we identified as 24.2 and 10 power minus 6. By substituting these values, the Reynolds number is 1.23 in 10 power 6. The critical value is given in the problem is 3.5 in 10 power 5. So up to these 3.5 in 10 power 5, it is laminar flow. Greater than a 3.5 in 10 power 5 and 1.23 in 10 power 6, it is a turbulent. So first, in case 1, when we are taking a value as a laminar flow, from the HMT data book from page number 113, we need to find the Nusselt number. So Nusselt number is 0.332, Reynolds number power 0.5, Prandtl number 0.0333. By substituting the Reynolds number value and Prandtl number value, we calculated the Nusselt number value. The Nusselt number of the general equation is HL by K. So therefore, Hx into L divided by K. By substituting this value, we can find the Hx value. Hx value is a local heat transfer coefficient. Hx is local heat transfer coefficient. H is the average heat transfer coefficient. Therefore, Hx is equal to 1.89 watt per meter square Kelvin. The average heat transfer coefficient H is equal to 2 into 1.89. So therefore, 3.78 watt per meter square Kelvin is the average heat transfer coefficient for a laminar. This is case 1. Next, case 2, when the flow will be a turbulent flow. from the turbulent flow, we need to take a new Nusselt number formula from the HMD data book of 114. Therefore, Nu is equal to 0.0296, Reynolds number power 0.8, Prandtl number power 0.33. By substituting the Reynolds number value and the Prandtl number value, we can find the new Nusselt number value is 1945. This is the general equation. Nusselt number general equation is Hx L by K. By substituting this new Nusselt number value, we can find the new Hx value is 21.22 watt per meter square Kelvin. This is the local heat transfer coefficient. For an average heat transfer coefficient is H is equal to 1.25 into Hx. In previously, in a laminar flow, from the local heat transfer coefficient, the average heat transfer coefficient formula is 2 into Hx. For a turbulent flow, 1.25 into Hx. Kindly note it. Here, for a turbulent flow, from local to average heat transfer coefficient, the formula is different. 1.25 into Hx. 1.25 into this 21.22 we can substitute. We can find the average heat transfer coefficient H is equal to 26.525 watt per meter square Kelvin. So now we solved a problem on a horizontal plate, that is problems on plate. Next problem, let's see a problem on a cylinder. This is a problem on cylinder. The problem given as an air at 15 degrees Celsius and 30 kilowatt per hour flows over a cylinder of 400 millimeter diameter and 1500 millimeter height with a surface temperature of 45 degrees Celsius. Calculate the heat loss. Here, the air temperature is given as 15 degrees Celsius. Therefore, T infinity is equal to 15 degrees Celsius and 30 kilometer per hour. Therefore, the velocity of the flow, the velocity value is given, we identify it is a forced convection. Therefore, the velocity U is equal to 30 kilometer per hour. Therefore, we need to find the values in terms of meter per second. So, kilometer to meter into 1000, hour into second divided by 3 to 600. By substituting this value, the velocity value is 8.33 meter per second. Therefore, the cylinder value, the diameter and height is given as an 400 millimeter, 1500 millimeter. So diameter D is equal to 400 millimeter. We need to convert it to meter. So divided by 1000, 0.4 meter. The length L is equal to 1500. So divided by 1000, 1.5 meter. The surface temperature is 45. The surface temperature is a wall temperature. So therefore TW is equal to 45 degrees Celsius. Calculate the heat loss. We need to find the heat loss. That is the Q value. Convective Q value we need to find. Right? So whatever the data, we need to find firstly the film temperature. We already seen in the previous problem itself. Therefore, T infinity is equal to TW plus T infinity divided by 2, 45 plus 15 divided by 2, therefore 60 divided by 2, 30. So from the property of air at 30 degrees Celsius from the HMD data book, we need to note down all these data, the density rho, kinematic viscosity gamma, Prandtl number PR, thermal conductivity K. From that, we need to find whether it is laminar flow or turbulent flow. So by finding a Reynolds number value, R is equal to UD by gamma, because it is a cylinder problem. If it is a plate problem like previous one, the Reynolds number formula is UL by gamma. Here, UD by gamma is a formula for Reynolds number because it is the problem of cylinders. Therefore, 8.33 into the diameter is 0.4. And the gamma is 16 into 10 power minus 6. Substituting this value, 2.08 into 10 power 5 is the Reynolds number value. So when we are solving problems on cylinder, the Nusselt number formula will be Nu is equal to C into Reynolds number power M, Prandtl number power 0.333. This is, we can take it from HMD data book at page number 116. This C and M. This C in a formula, there will be a two new terms C and M. This C and M we can take it in from by Reynolds number value. There will be a slab for a Reynolds number. If the Reynolds number is less than 2.0 into 10 power 5, we can take it as C is equal to 0.0266 and M is equal to 0.805. By substituting this C and M in the formula Nusselt number, we can find the Nusselt number value is 451.3. Right? We know the Nusselt number general equation HD by K because it is a problem on cylinder. If it is a problem on plate, is HL by K. Therefore, N is equal to HD by K. By substituting this Nusselt number value, and we know the D value and we know the H value, by substituting all these value, the only unknown data is H. The H is the heat transfer coefficient. H is equal to 30.18 watt per meter square Kelvin. In this problem, we need to find the heat loss, that is Q. We know the general equation Q is equal to HA into TW minus T infinity. We know the value of H 30.18. We know the value for A. The formula for A is, it is a cylinder. Cylinder surface area formula is pi dl. We know the D value, we know the L value. Phi is the constant value 3.14. TW and T infinity in the problem is in the given data itself is given. Therefore, by substituting all these known data, the only unknown data is Q. Therefore, Q is equal to 1706.6 watt is the heat transfer value for cylinder, right? So this is the problem of cylinders. And next, we need to solve a problem on sphere, right? Third problem. Let us see the problem. The air at 30 degrees Celsius and 0.2 meter per second flows over a 120 watt electrical bulb at 130 degrees Celsius. The air at 30 degrees Celsius means the temperature of the air, that is the fluid temperature. T infinity is equal to 30. 0.2 meter per second means velocity. If the velocity is given, then the problem will comes under the force of convection. We identify. Therefore, velocity is equal to 0.2 meter per second across the electrical bulb of 120 watts. That is the energy generated by lighting an electrical bulb is 120 watts. Therefore, Q1 is equal to 120 watts at a temperature of 130 degrees Celsius. The bulb temperature with surface temperature. TW is equal to 130 degrees Celsius. Find the heat transfer and power loss due to convection. The bulb diameter 70 degrees Celsius. We need to find the heat transfer value Q and the power value when we are solving in a convection if the bulb diameter is 70 millimeter. So the diameter of the bulb D is equal to 70 millimeter. We need to convert it to meter divided by 1000, 0.07 meter. We need to find the heat transfer power loss due to convection. So first, whatever it may be, the first we need to find the flame temperature. TF is equal to TW plus T infinity divided by 2. 130 plus 30 divided by 2 is 160 divided by 2, therefore 80. So from the property of air at 80 degrees Celsius, from HMD data on page number 34, we need to note down the parameters called density and kinematic viscosity, Prandtl number and thermal conductivity. And we need to find the Reynolds number value as usual, like in previous problem. So Reynolds number RE is equal to U d by gamma because it is a problems of sphere. Therefore, it also a U d by gamma. For sphere and cylinder, the formula for Reynolds number is U d by gamma. For plate, it is U L by gamma. Therefore, we know the U value, D value, and gamma value. We need to we can find it. We can calculate the Reynolds number value is 663.83. From the HMD data on page number 120, the Nusselt number formula is 0.37. Reynolds number power 0.6. We know the Reynolds number value, like from previous step. We can substitute the Reynolds number value and find the Nusselt number value is 18.25. The Nusselt number formula is HD by K. We know all the parameters except H. That is the heat transfer coefficient. The heat transfer coefficient H is equal to 7.94 watt per meter square Kelvin. So from that we need to find the first one, heat transfer, like previous one. Q is equal to HA into TW minus T infinity. H is, we can calculate as previous step 7.94. What is the area? Area formula is, here it is a surface area for a sphere, therefore 4 pi r square. Previous problem, it is pi dl because that the problem is comes under cylinder. So this problem comes under sphere. The electrical bulb is in the shape of sphere. Therefore, 4 pi r square and TW T infinity in a problem itself given. By substituting all these value, we can calculate the Q value as a 12.22 watts. That is the heat transfer value. And second term, we need to find the power loss. Power loss means the total power is 120 watts of electrical bulb. Here, this is the heat loss, that is 12.22. So for how we can find the percentage of heat loss is equal to Q2 divided by Q1 into 100. What is the Q2? That is the heat loss is the Q2. Therefore, 12.22 divided by what is the Q1? The electrical bulb watts is given in a problem is 120. Therefore, 12.22 divided by 120 into 100, the percentage will be 10.18. If the bulb diameter is 70 millimeter, the heat loss will be 12.22 watts. The percentage of heat loss will be 10.18%. So these are all the problems. We are solving problems on an convection or forced convection for plates, cylinder, and sphere. Right? Thank you. Let us see a new topic in the next class. Thank you.